This video presentation will describe the theory and measurement of P25 C4FM modulation fidelity using the Aeroflex 3920 digital radio test set. Measurement techniques for analog modulation schemes, such as FM and AM, are based upon the inherent analog nature of the modulating signal. Whether the modulation is FM or AM, the characteristics impressed upon the carrier are an analog of the modulating signal. The system defined by the TIA-EIA 102 P25 standard, however, is a digital system that encodes and decodes all content, including voice and signaling, as a binary stream of ones and zeros. The modulation scheme employed in the transmission of this digital data relies on a number of parameters that cannot be measured using standard analog equipment. For example, modulation fidelity, a very important measurement of the P25 standard, requires specialized equipment such as the 3920 digital radio test set. Before delving further into the modulation fidelity measurements, we'll first review how the P25 modulation works. P25 uses a type of FSK modulation called C4FM. C4FM is an acronym meaning Compatible 4-Level Frequency Modulation. C4FM is a type of 4-level frequency shift keying developed for the P25 standard. As the name implies, the carrier will always be in one of 4 deviation or frequency shift states. Consider this spectrum analyzer display. The horizontal axis represents frequency. The unmodulated carrier is in the center frequency of its channel. This chart represents the 4 states of the C4FM modulation. Likewise, the horizontal axis represents frequency. The red vertical line indicates the center frequency of the channel. Each of the vertical black lines represents a frequency offset from the center frequency of the channel. The frequency offsets are minus 1800 Hz, minus 600 Hz, plus 600 Hz, and plus 1800 Hz. Each offset frequency represents a symbol. Each symbol consists of 2 bits of data. A minus 1800 Hz frequency offset represents the symbol 11. A minus 600 Hz offset represents the symbol 10. A plus 600 Hz offset represents the symbol 00. And a plus 1800 Hz offset represents the symbol 01. The carrier is illustrated as being at the center frequency, which does not represent a symbol. In practice, the carrier will always shift between the 4 defined frequency states. When the carrier shifts to a minus 600 Hz offset from the center of the channel, this represents the symbol 10. A plus 1800 Hz carrier offset represents the symbol 01. A minus 1800 Hz carrier offset represents the symbol 11. And a plus 600 Hz carrier offset represents the symbol 00. The frequency shift information is transmitted at the symbol rate of 4800 symbols per second. Each symbol represents 2 bits of data, so the bit rate is 9600 bits per second. Modulation fidelity is an indication of the quality of the signal being transmitted by the radio. The EIA-TIA 102 P25 standard defines modulation fidelity as the degree of closeness to which the modulation follows the desired theoretical modulation. Rather than being just one measurement, modulation fidelity is a combination of a number of parameters including frequency error, symbol deviation, and RMS deviation error. Frequency error refers to the RF carrier frequency accuracy. A carrier frequency error would tend to shift all 4 deviations by the same amount. To determine the frequency error, we find the average frequency deviation for each of the 4 deviation points and then calculate the average over 144 symbols. In this example, the carrier has a positive offset. The frequency offset of each data point is averaged over 144 symbols. The average measured frequency deviation is then averaged over the 4 points to arrive at a frequency error of 100 Hz. In contrast, an analog frequency error meter would count the average frequency of the signal by counting the number of cycles in a given period. Say, for example, the signal contains a large number of zeros. The average deviation detected by an analog counter would include a large number of counts with a 600 Hz offset. This would skew the results with an erroneous reading. Thus, an analog offset meter cannot be used for this measurement. By the same token, a zero-crossing frequency error meter relies on equal distribution of the deviation points. The distribution points of the C4FM signal are rarely equally distributed, so the zero-crossing frequency error meter will also produce misleading results. The frequency error of the carrier shifts the deviation of data points globally in the same direction. However, each data point will have its own amount of deviation error as well. The symbol deviation meter is used to provide a measurement of the average deviation of the data points. Before starting the calculation, the frequency error is removed from the average measured deviation values that were used to determine the frequency error. After the frequency error is removed from the deviation measurements, each symbol's deviation is divided by the ideal deviation to produce a deviation ratio for each symbol. Next, the average deviation ratio is calculated for all four symbols. Before the value is displayed, the ratio is multiplied by 1800. Thus, the symbol deviation is not just a measurement of the 1800 Hz deviation symbol, it is actually an aggregate of all the symbols. The last value calculated from the measured deviation of each symbol is called RMS deviation error. On the Aeroflex 3920, this measurement is labeled as modulation fidelity in accordance with TIA EIA-CAAB-C, section 3.2.16, where table 3-18 is labeled modulation fidelity limits. RMS deviation error is an indication of how much the symbol deviations vary from their ideal values over 144 symbol periods. As with the deviation measurement, the frequency error is first subtracted from each symbol. The modified deviation figure is then divided by the deviation ratio that was calculated by the deviation measurement. The ideal deviation is then subtracted from the modified deviation. The difference between the modified deviation figure and the ideal deviation is then squared. This process is repeated 144 times per measurement. The 144 different squared calculations are then summed together. The summed square difference figure is averaged over the 144 symbols. The RMS deviation error is the square root of the sum and is expressed as a percentage of 1800 Hz. The UUT measurements tile displays the numerical results of the modulation fidelity measurements. In addition to the numerical displays, the instrument provides 3 graphical displays that provide a visual dimension to these measurements. The constellation display provides 4 green circles for identifying the ideal locations for each of the measured deviations. A perfect signal would show a single dot in the center of each circle, though in reality there is usually a line that shows the spread of deviation for each symbol. In this example, the signal has a low symbol deviation but acceptable RMS deviation error. The deviation points are narrow, but do not line up well with the target deviations. In this example, the signal has a high symbol deviation but acceptable RMS deviation error. The symbol deviation of this signal may measure within limits, but the RMS deviation error is quite high. Like the constellation display, the distribution plot shows the deviation of each symbol. The horizontal alignment of each peak to the vertical dotted lines corresponds to the alignment of each deviation point to the ideal position. The horizontal width of each point is a function of the RMS deviation error of the signal. However, the function of the amplitude of each peak provides additional information not found in the constellation display. The vertical axis indicates the number of times the signal deviates to each deviation. The high peak at the plus 1800 Hz deviation point indicates that the signal is deviating more often to that point than, say, the plus 600 deviation point, which has a much lower peak. This signal is a standard 1011 pattern. Note that the signal deviates to the plus 600 Hz deviation far more often than to the other deviations. A signal with low symbol deviation will shift the peaks inward on the horizontal axis. A signal with high symbol deviation will spread the peaks outward. A signal with high RMS deviation error becomes obvious as the peaks spread out on the horizontal axis. Whereas the constellation diagram and distribution plot show the demodulated signal at the symbol points, the eye diagram displays the demodulated signal at all points. The horizontal axis of the eye diagram represents time. The vertical axis of the eye diagram represents deviation. The four horizontal dashed lines represent the deviations at the various symbol points. The vertical lines and the start-stop of the graph are the locations at which the graph goes through a symbol point. With a good P25 signal, the line should cross precisely through the point at which the vertical and horizontal lines meet. A signal with low symbol deviation will have imprecise crossing points. Likewise, a signal with high symbol deviation will miss its target points. A signal with high RMS deviation error produces a wide variance in the symbol point crossings. The instrument's P25 test tile can be configured in a number of ways to obtain at-a-glance comprehensive views of test criteria. In this example, the UUT measurements tile is displaying the three main parameters of modulation fidelity: frequency error, symbol deviation, and RMS deviation error, displayed here as mod fidelity. The eye diagram, constellation display, and distribution plot are also selected for display. The input signal has near-perfect modulation fidelity characteristics. The symbol deviation has dropped from 1800 Hz to around 1600 Hz. The symbol deviation meter and graphical displays reflect the low symbol deviation. The RMS deviation error and frequency error meters indicate those parameters are still quite good. The symbol deviation is now nearly 2 kHz. The symbol deviation meter and graphical displays reflect the high symbol deviation. Again, the RMS deviation error and frequency error meters indicate those parameters are well within the norm. The incoming signal now has an RMS deviation error of over 6%. The mod fidelity meter and graphical displays reflect the high RMS deviation error. Though the RMS deviation error is high, the symbol deviation and frequency error are well within acceptable limits. The signal now has a 2 kHz frequency error. Note that, though the signal has a significant frequency error, the graphical displays and deviation meters are largely unaffected. Remember that the first step in calculating symbol deviation and RMS deviation error is to eliminate the frequency error of the carrier. So, although the symbol deviation and RMS deviation error are well within acceptable limits, it is important to remember that this vital parameter will still affect modulation fidelity.